Let's get into it. Number 10. The Ice Mountains. On July 15, 2015, one day after closest approach, the New Horizons team released the first detailed photograph of Pluto's surface. LORRI, the long-range camera, had captured something nobody predicted. Mountains. Water ice mountains standing 3.5 kilometers above the surrounding plains, roughly 11,000 feet. At minus 235 degrees, Celsius water ice does not melt or compress. It behaves like granite. Rigid, load-bearing, strong enough to hold peaks that rival the Rockies. The team named the tallest range Tenzing Montes after Tenzing Norgay, who summited Everest in 1953. A smaller range nearby became Hillary Montes after Sir Edmund Hillary. Both sit along the southwestern edge of a vast heart-shaped basin where smooth nitrogen ice meets fractured highland bedrock. Ralph the infrared spectrometer confirmed the boundary. Nitrogen ice on one side, water ice on the other. A razor-sharp contact zone between two entirely different materials. The soft nitrogen fills the basin and flows around the rigid water ice mountains like a frozen sea pressing against a coastline. Ancient bedrock next to basin ice young enough to be measured in millions of years. Geologists expected a uniformly cratered dead surface. Instead, they found distinct geological provinces with active boundaries and no tectonic plates to explain them. Between these peaks, the terrain changes. East of the heart-shaped basin, the ground turns into something no geologist had a name for. Number 9. The bladed terrain. A methane ice spire 500 meters tall. Then another beside it. Rows of identical blades stretching to the horizon spaced 3 to 5 kilometers apart. This is Tartarus dorsa. Geoffrey Moore at NASA Ames led the analysis and identified these structures as penitents. On Earth, penitentes are delicate snow spikes a few feet tall found in the high, dry Andes. Sublimation carves them. Sunlight converts surface ice directly into vapor without melting it first, and the geometry of the erosion creates jagged ridges. On Pluto, the same physics runs at a scale hundreds of times larger. LORRI captured the snakeskin texture at high resolution. Ralph confirmed the composition. Methane ice sculpted over millions of years by faint ultraviolet light arriving from 3.6 billion miles away. One question remains unsettled. Methane ice is soft. Whether pure methane can support 500-meter vertical structures without sagging under its own weight is an open problem. Moore's team proposed an alternative, methane clathrate, a rigid lattice of water ice with methane molecules locked inside the crystal structure. Clathrate is far stronger and could explain how the blades survive intact. No other body in the solar system except Earth hosts penitents. Finding them here forced planetary scientists to accept that sublimation erosion operates wherever the right ice meets the right angle of sunlight. Scale changes. Physics does not. Sublimation built the blades by carving ice away. The carved grains had to go somewhere. Wind carried them. That raises a question nobody expected to ask about a world this small. Number 8. The methane dunes. Where the foothills of the Great Mountains meet the nitrogen ice plains, New Horizons found parallel ridges spaced evenly across flat terrain. The pattern was unmistakable dunes, built from tiny grains of frozen methane. The problem is atmospheric density. Pluto's atmosphere is roughly 100,000 times thinner than Earth's. Surface pressure sits near 10 microbars. At that density, wind should lack the force to push solid grains across a surface. Every textbook said so. Matt Telfer at the University of Plymouth led the study published in Science in 2018. His team solved it. Nitrogen ice on the surface sublimates when sunlight hits and the escaping gas creates a thin, fast layer of wind hugging the ground. just enough force to loft small methane grains and roll them downhill from the nearby mountain slopes where methane snow accumulates and fractures into fine particles. Transverse dunes. Ridges running perpendicular to the wind direction. Identical geometry to sand dunes in the Sahara. Physics scales differently. Aerodynamic result is the same. Before Telfer's paper, atmospheric scientists assumed a minimum surface pressure threshold below which wind could not transport particles. Pluto shattered that threshold by several orders of magnitude. Mars, Triton. Kuiper belt objects not yet visited. The dunes forced recalculation for all of them. Wind requires an atmosphere. Pluto was not supposed to have one worth measuring. Number 7. The atmosphere. Pluto is smaller than Earth's moon. Escape velocity barely reaches 1.2 kilometers per second. A body this small and this cold should hold nothing above its surface except vacuum. After closest approach, the spacecraft turned and looked back at Pluto with the sun behind it. ALICE, the ultraviolet spectrograph, recorded the light filtering through the limb. REX, the radioscience experiment, measured pressure and temperature profiles. What they found was a nitrogen-dominated atmosphere with traces of methane and carbon monoxide extending more than 300 kilometers above the surface. ALICE detected at least 20 distinct horizontal haze layers. Some stretched for hundreds of miles in clean parallel bands visible against the backlit limb. The haze particles are tholins. Ultraviolet light cracks nitrogen and methane molecules apart high in the atmosphere. The fragments reassemble into complex organic hydrocarbons. They clump. They drift downward like slow chemical snowfall, and they're small enough to scatter blue light. The processed images showed a blue sky. Genuinely blue, for a different physical reason than Earth, but visually almost identical. Those haze layers solved a separate mystery. Pluto turned out to be colder than predicted. Tholin particles radiate infrared energy to space more efficiently than the gas around them. That extra cooling pathway was missing from every atmospheric model written before 2015. As the particles grow heavier, they fall to the ground and stain the surface reddish-brown. Pluto's dark regions get their color from above. Its own atmosphere manufactures organic pigment and drops it onto the landscape. That atmosphere does not stay put. Pluto's gravity leaks gas into space. Where it ends up is one of the stranger chemical stories in the solar system. Number 6. Charon's red cap. Pluto's largest moon hangs 12,000 miles away, tidally locked, gray, cratered, geologically quiet, except at the North Pole where a dark reddish stain covers the cap like dried residue on stone. Charon has almost no atmosphere of its own. It cannot manufacture tholins. Will Grundy at Lowell Observatory published the explanation. Methane escaping from Pluto's atmosphere drifts across the gap, and a fraction reaches Charon. Most of the moon is too warm for the gas to stick. During Charon's long winter, each pole spends decades in continuous darkness at temperatures near 15 Kelvin, cold enough to freeze methane on contact. Once frozen, the methane sits exposed to Lyman alpha ultraviolet photons scattered by interplanetary hydrogen and to charged particles from the solar wind. Both energy sources crack the methane apart. Fragments reassemble into heavier organic chains, tholins. When spring returns and sunlight reaches the pole, the lighter methane sublimates and escapes. The tholins are heavier and heat-resistant. They stay put. Each winter deposits fresh methane. Each winter cooks it into dark organic residue. Each spring strips away the volatile fraction and leaves the residue behind. Millions of years of that cycle built the permanent varnish Grundy's team confirmed from spectral data. Pluto breathes onto its moon, and the breath leaves a permanent stain. Remember those haze particles falling on Pluto from number 7. Same tholin chemistry. Soy the same molecular family. Different delivery system. Both processes run through Pluto's leaking atmosphere, and that atmosphere connects to something larger. Parts of Pluto's surface carry almost no craters on terrain 4.5 billion years old. Something keeps scrubbing the record clean. Number 5. The churning plains. Sputnik Planitia is a basin the size of Texas filled with nitrogen ice. It sits 3 kilometers below the surrounding terrain. When Lori photographed it at high resolution, the images showed a pattern. Polygon shapes, cells 10 to 30 miles across bordered by narrow troughs. Oliver White at the SETI Institute and collaborators at Washington University and the CNRS in France identified the mechanism: solid-state convection. The nitrogen ice layer runs an estimated 3 to 6 kilometers deep inside the basin. Internal heat warms the bottom layer just enough to make it buoyant. Warm ice rises. Cooled ice at the surface sinks along the trough boundaries. The entire basin overturns in slow motion. One full cycle takes roughly 500,000 years. Fast enough to erase impact craters before the bombardment can build a visible record. The surface appears effectively brand new, less than 1 million years old. A study published in Nature added a second driver. Sublimation at the surface cools the top of the nitrogen layer and steepens the temperature gradient. Heat pushing up from below, cold pulling from above. 2 engines running the same convective machine. Between them they keep the plains young and the crater count near 0. Step back for a second. Mountains from number 10 are ancient bedrock. So dunes from number 8 are recent deposits. Convection cells here are active right now. Pluto's surface spans multiple geological epochs existing side by side. Convection requires heat. So does what sits just south of this basin. Domes built by eruption, and the eruptions happened recently. Number 4. The Cryovolcanoes. Wright Mons rises 5 kilometers above the surrounding plains, 150 kilometers across, wider than Mauna Loa. Next to it, Picard Mons stands 7 kilometers tall and stretches 225 kilometers wide. Both are domes built entirely from erupted ice. Kelsey Singer at the Southwest Research Institute led the study published in Nature Communications in 2022. Her team found the region around both structures is nearly free of impact craters. In geological terms, the eruptions might as well be yesterday. Early reports called the central depression on Wright Mons a caldera. Singer's analysis pushed back. No collapsed terraces, no radial flow channels. The structure appears to be the merger of multiple smaller eruptive centers that grew and fused over time. The erupted material is water ice with the compressive strength of terrestrial rock at these temperatures, strong enough to hold domes this size without slumping. The eruptive fluid was likely a slush of water ice and ammonia with antifreeze compounds lowering the melting point enough to mobilize material from depth. The volume involved exceeds 10,000 cubic kilometers across both structures. For context, that is larger than Lake Erie. Building these domes required a reservoir of liquid or near-liquid material underneath the crust. Singer's paper made the implication explicit. Ice volcanoes this large and this recent demand a warm interior. Remember the convection cells from number 5. Heat from below drives those too. Both features require the same thing, and that thing is the most controversial discovery on this list. Number 3. The hidden ocean. 3.6 billion miles from the sun. Surface temperature minus 230 degrees Celsius. Every thermal model written before 2015 concluded Pluto should be frozen from crust to core. A solid ball of ice and rock with no internal activity. The fractures told a different story. Pluto's crust shows extensional faults stretching across ancient terrain. Almost no compression features exist anywhere. If the entire interior had frozen billions of years ago, the expansion of water crystallizing into ice would have compressed and buckled the shell. Instead, the shell has been stretching, slowly, steadily. Freezing is still underway. That means liquid water still exists beneath the ice. Alex Nguyen and Patrick McGovern at the Lunar and Planetary Institute published a study in Icarus in 2024. They modeled stress patterns around Sputnik Planitia and calculated the ocean density from fracture geometry. 8% denser than Earth's seawater, comparable to the Dead Sea. The rocky core measures about 1,700 kilometers across, 70% of total diameter. Bulk density sits at 1.86 grams per cubic centimeter, to 60 to 70% rock by mass, far more than anyone assumed for an icy Kuiper belt dwarf. Radioactive decay in that rock has ticked for 4.5 billion years. The output is small but steady, and the ice shell above insulates it. A 2025 study in Nature Geoscience added a second heat source. The ancient collision that captured Charon may have deposited enough tidal energy to warm the interior early in Pluto's history. A hot start, not a cold one. Alan Stern, the principal investigator for New Horizons, continues to push for a dedicated orbiter carrying ice-penetrating radar to settle the question by direct measurement. An ocean under the crust, volcanoes on the surface, an atmosphere staining the landscape red, mountains rivaling the Rockies, dunes in an atmosphere thinner than a laboratory vacuum. Got all of it on a world classified as inert. Then in 2016, a telescope detected something from Pluto that made physicists stop and recheck their instruments. Number 2. The X-ray signal. Pluto has no magnetic field, no internal fusion, no known mechanism for producing high-energy radiation. In 2016, Carrie Lease at the Johns Hopkins Applied Physics Laboratory announced that the Chandra X-ray Observatory had detected X-ray photons coming from Pluto. 4 separate observations between 2014 and 2015 confirmed the signal. Charge exchange is the proposed mechanism. Heavy ions in the solar wind collide with neutral gas molecules escaping Pluto's atmosphere. When an ion captures an electron from a neutral molecule, the energy difference is released as an X-ray photon. Well documented at comets. Solar wind hits the coma, and the interaction glows in soft X-rays. At Pluto, the math collapses. Solar wind intensity at 40 astronomical units is far weaker than the wind hitting inter-system comets. SWAP and Pepsi. The particle instruments aboard New Horizons had just measured Pluto's atmospheric escape rate. Low, stable, controlled. Far less gas streaming into space than old models predicted. Less wind, less target gas. Both factors should have made the signal undetectable. Chandra measured a brightness higher than any model produced. Something about the interaction geometry or the local particle environment at that distance amplifies charge exchange beyond current predictions. First X-ray detection from any Kuiper belt object. The mechanism that generates the photons is understood, the intensity is not. So open problem. Every discovery on this list connects to one geological feature, a basin shaped like a heart that drives the atmosphere, feeds the dunes, paints the moon, keeps the plains crater-free, and it has a pulse. Number 1. The beating heart. Nitrogen ice inside Sputnik Planitia sublimates during the long Pluto day when weak sunlight heats the surface. The gas flows outward. At night, the nitrogen condenses back into ice. Tanguy Bertrand at NASA UMS modeled the full atmospheric circulation and published the results in the Journal of Geophysical Research in 2020. The heart pumps nitrogen gas outward during daylight hours. That gas flows westward, against the direction of Pluto's rotation. At night, it flows back. Bertrand's team called it retrorotation, almost unique in the solar system. And only Triton might share a similar pattern. Wind streaks visible in New Horizons images fan outward from Sputnik Planitia like spokes on a wheel. Dark haze particles carried by the nitrogen winds settle in directional streaks that point back toward the basin. The entire atmospheric circulation pattern traces to this single reservoir of nitrogen ice. The winds do more than push particles. Sublimation cools the basin during the day. Condensation releases latent heat at night. That thermal pump helps regulate Pluto's climate on a global scale. One basin controlling the temperature budget of an entire world. Then there is the gravitational consequence. Sputnik Planitia likely formed as an impact basin and over time accumulated enormous mass in nitrogen ice. So that mass concentration created a gravitational anomaly heavy enough to physically reorient Pluto. The basin migrated toward the tidal axis facing away from Charon. The heart did not end up in its current position by chance. It pulled the planet until the planet shifted to accommodate it. A single geological feature that drives the atmosphere, feeds the wind, paints the surface, controls the temperature, and moved the world carrying it. Every item on this list, from the mountains to the X-rays, connects back to a planet that was declared dead and then refused to cooperate. New Horizons photographed roughly 40% of Pluto's surface at high resolution. The other 60% remains unseen. Whatever is hiding on the far side may be stranger still.